cryptography encryption. You generate some secret keys and some public keys, and you turn your gossip into gibberish. You send it over the internet. If your boss wants to figure out what the gossip is about, then they only see the gibberish and the public keys. And to get back the gossip, it takes the scheme is made so that they have to solve a very hard problem. And what does hard problem mean? It means that we think, at least, we expect there not to exist any algorithm that solves it in polynomial time, in the length of the inputs. So some examples are the discrete logarithm problem, it's given there, or factorization of large numbers, and as you see here, Diffie-Hellman RSA, these are things that were actually implemented. This is how the internet works today. But as Nihar also pointed out, there's also post-quantum cryptography. Thing is, there might be a future where there's big quantum computers, and Shor showed that these problems are actually easy for a quantum computer. So we looked for some other problems, people looked, and there's some coming from isogeny, some super singular elliptic curves, and some come from lattices, as Nihar pointed out. One problem is the shortest vector problem. It's just really given any lattice, could be very skewed and whatever. Just compute the shortest vector or the length of it. Or maybe compute a short-ish vector. Good quality sort of vector. Yeah, these things actually give rise to protocols, and there's a whole competition to standardize them. This will actually be the future of cryptography. There's also drama. It's quite an interesting field at the moment. And yeah, what I'd like to talk about is hardness of these problems. And what I said is that we expect them to be hard for quantum computers even. That means that if I give you an algorithm that tries to solve all instances, there's at least one instance of the problem where it fails. That's what we expect. However, in the real world, I told you, like me and Edgar, we had to generate some keys. And we generate them from some distribution, kind of generate them randomly. But maybe this distribution is bad. Maybe it constantly gives you, or with very high probability, it gives you instances of the problem that are easy. There's maybe already some algorithms out there that do some cases. So which random distribution do we choose so that this average case, so for the randomly generated instances, is this problem still hard? So we want to show that the average case problem is still essentially as hard for a well-chosen random distribution. As I said, we think this is hard, so basically then the average case should also be hard. Contraposition, assume average case is easy, and show, this is a typo, show that the worst case is easy. How do you do this? This is, in computer science, it's called reduction. What we want to do is just solve the arbitrary case, the worst case. So take an arbitrary instance. What do we have? We have an oracle, a black box that just solves random instances. So do something to this arbitrary instance, shake it around so that you get something random, plug it into your black box. This will be really good at giving you a solution. So with high probability, you get a solution that's of good quality. And be clever enough so that you can kind of reverse this thing and get a solution back for your arbitrary instance. This is a scheme, a sort of general scheme of a reduction, and it's the one that I'll use in, well, we use in my collaboration with some people. I'll show in a bit. Now, what's a useful average case? Nihar also already pointed out, what's the space of lattices? Well, it's really just given by, or let's say unimodular lattices, given by SLNR mod, SLNZ, and I think most of you here maybe only know one nice distribution, like probability measure on this thing. Just take the normalized R measure. Funny enough, it turns out it's actually a good choice. Because, for instance, lattices that are very skewed, that are kind of come from the cusp, they're easy to deal with. You can find short vectors fairly fast. But we know that the Haar measure gives very little volume to the cusps. So that's a good contender. And what we'll do to show that it's actually still as hard as or essentially as hard as the arbitrary case, as the worst case, is we'll use Hecke equidistribution, which we've also talked about today. The idea is, as I said, we need to start with with an arbitrary lattice. Could be anything. And we need to randomize it somehow. And okay, what we'll do is we need to also deform it a little, just wiggle it around in the sort of in a geometric sense, or at the Archimedean place, I say. But basically what you do is you take a random sublattice of a large index. It turns out, what is a Hecke operator at the level of functions, taking a random sublattice of index p means applying TP. TP is really just averaging over all the sublattices of index p with equal, with uniform probability. And we've said already that Hecke points equidistribute. This is this idea behind Hecke equidistribution, or the equidistribution of the Hecke correspondence. Yeah, it's been studied. It's like one of these most important equidistribution problems at the turn of the century. In my work, I use the approach of Clauzel-Ullmann. So it comes from the spectral gap of Hecke operators. All right, so now we managed to, let's go back just one sec. We did this part. Apply the black box magic. You get a solution. You get a short vector where in a sublattice of your original lattice. But, I mean, that's already a vector in the lattice that you started with. So if you're optimistic enough, that's already also a short vector in your original lattice. Of course, you have to make this quantitative. It won't be always a good short vector, a good quality solution. What you do mathematically, I don't know, maybe 2 minutes. Okay, whatever.
3 minutes.
You just, you do mathematics. So you do a kind of automorphic kernel that kind of looks like a bump function around your around your lattice. That's basically like this wiggling around this function, and then you apply TP. And saying that we'll look at in the end like a random lattice means this quantity here goes to 0. And it should go to 0 fast enough because we're talking about algorithms. We want to theoretically maybe implement this. So it should be fast, polynomially fast in whatever parameter you're interested in. What is this here? So by the way, I should say this is under Ramanujan. Really, there should be this theta there, like 1 minus 1 half plus theta. But computer scientists are willing to assume everything. And what we need to understand is this part, actually. So we get this, that p goes to infinity, this will go to 0, but how fast? Well, this norm is actually quite interesting to study. It tells you how far you are in the cusp, really. It's big in the cusp, and that makes sense. If you start in the cusp and you start taking Hecke neighbors, it will take you ages to get down to the bulk where most of the random lattices live. If you take a skew lattice, very skewed lattice, and you take a sublattice, it will still be skewed if p is not large enough. But as I said, we might actually get, so we have several challenges that are interesting. And the other challenge is the quality of the solution. If you take a shortest, if I just give you the shortest vector in this sublattice, 1,000 times z squared, that has length 1,000, but inside this lattice, which is the original arbitrary lattice, well, we were looking for something that's close to 1, so that's already bad. You shouldn't be taking p too large, and you shouldn't be taking your lattice too skewed. So you have to give other algorithms. Actually, we have to piece together 2 other algorithms, and we can't even do it for general lattices. We need to reduce to just looking at modular lattices, as Nihar said. So these are just lattices with extra structure coming from number fields. And we can do the degree of the number field aspect, generalizing some work that they had with some collaborators for ideal lattices. We can fix the rank of the lattice, but the rank has to be fixed as a module over your number field. And that's how you use Hecke distribution in computer science. That's all that I want to say.